Differential geometry for spacetime begins from a very quiet but very powerful idea. When we first learn special relativity, we are often introduced to a very elegant picture of the world. Space and time are joined into a single structure. Events are points in this structure. Light traces out special paths. Moving observers describe the same physical reality in different coordinate systems, yet the underlying geometry remains fixed. This setting is beautiful, coherent, and deep. It already teaches us that time is not separate from space in the old intuitive way. It teaches us that simultaneity depends on motion. It teaches us that geometry and physics are intimately connected. But as beautiful as this flat spacetime picture is, it is not enough for gravitation. Let us begin there, because it is worth understanding not only what differential geometry is, but why it becomes necessary. In the flat spacetime of special relativity, geometry is fixed once and for all. It has the same structure everywhere. No region is more curved than another because there is no curvature at all. One can choose many coordinate systems, and some of them may look more complicated than others, but beneath those descriptions the spacetime remains globally flat. It is like an idealized stage that never bends and never responds to the matter upon it. Gravity does not fit comfortably into that picture. The great conceptual shift of general relativity is that gravitation is not merely a force acting inside spacetime. Rather, gravitation is tied to the geometric structure of spacetime itself. Matter and energy do not simply move through a passive background. They influence the background. The very arena of physics acquires flexibility. It can bend. It can curve. It can vary from place to place. And once we admit that spacetime may curve, flat Minkowski space is no longer general enough. We need a broader language. We need a kind of space that, on small scales, still allows calculus and local measurement, but on larger scales may have a complicated global shape. We need a framework in which one can talk about local coordinate systems without mistaking them for the space itself. We need a setting in which tangent directions, derivatives, curvature, and the geometry of motion can all be defined without relying on a single global Cartesian grid. This is why manifolds are needed. A manifold is, in essence, a space that looks locally like ordinary Euclidean space, even if globally it may be much more intricate. This local resemblance is the key. It allows us to borrow the tools of calculus from familiar flat space, but use them in a much more flexible geometric setting. It is helpful to think first of ordinary surfaces. A sphere is not the same as a plane. Globally, the two are different in obvious ways. A sphere closes up on itself. It has no edges. It bends in a way a plane does not. And yet if one looks at a small enough patch of a sphere, that patch resembles a piece of the plane. It is not exactly the same in a strict geometric sense, but it is close enough that one can place coordinates on it, measure directions, define curves, and do calculus locally. This is the guiding idea behind manifolds, but in a much more general setting. A spacetime manifold is not simply a bent surface sitting inside some larger space. It is a geometric object in its own right. One should not imagine that it must always be embedded inside some higher dimensional room. The manifold itself is the mathematical stage. It carries the information we need intrinsically, meaning from within its own structure. That is worth repeating. A manifold is not just a shape drawn inside something bigger. It is a space that can be understood from the inside, patch by patch, using local coordinates that fit together consistently. This is exactly the flexibility that gravitation requires. Spacetime in general relativity may be curved by the distribution of matter and energy. Different regions may have different geometric properties. Paths of free motion may bend not because a force pushes objects in the old Newtonian sense, but because the geometry itself guides motion. To express this clearly and rigorously, we need the language of manifolds. Let us pause and reflect. First step, then, is not curvature itself, and not yet gravity in full detail. The first step is to enlarge our notion of space. We move from a single fixed flat model to a class of spaces that are locally simple but globally flexible. That is the move from flat spacetime alone to manifolds. Once this idea settles, coordinates can be reinterpreted properly. In elementary mathematics, coordinates often feel like the space itself. A point in a plane is described by two numbers, and it is easy to slip into thinking that the numbers are the point. But in geometry, especially in relativity, this is too naive. Coordinates are descriptions. They are labels. They are useful, often essential, but they are not the underlying reality. A manifold may be described using many different coordinate systems. No single one is privileged in principle. What matters is the geometry, not the labeling scheme. To make this precise, one introduces charts. A chart is a local coordinate description of part of the manifold. It takes a region of the manifold and assigns to each point in that region a list of numbers. Those numbers behave like ordinary coordinates in Euclidean space. Inside the domain of the chart, one can then perform calculus just as one does in familiar flat settings. But because a single chart may not cover the entire manifold, we use many charts. An atlas is a collection of charts that together cover the manifold. Where two charts overlap, their coordinate descriptions must be compatible. That means one can translate from one coordinate system to another smoothly. This compatibility is not an afterthought. It is the heart of the construction. Without it, the local descriptions would not fit together into a coherent geometric object. So a manifold is built, in practice, from many local coordinate windows, each resembling Euclidean space, all stitched together in a smooth way. This is a very gentle but profound idea. We are saying that one need not insist on a single universal coordinate system. Instead, one accepts many local descriptions, provided they agree appropriately where they overlap. This gives enormous flexibility. It also reflects physical wisdom. Different observers, different choices of coordinates, even different practical computational schemes, may describe the same spacetime. The spacetime itself is not changed by the labels. It is worth repeating that geometry must not depend on the chosen coordinates. This principle appears again and again in differential geometry and relativity. Coordinates are tools. They are not the content of the theory. A good geometric statement should remain meaningful no matter which allowed coordinates are used. If a property appears in one coordinate system and disappears in another, then one must ask carefully whether it is truly geometric or merely an artifact of description. In this way, the use of charts and atlases trains us to separate the intrinsic from the accidental. Once we accept that manifolds are spaces described locally by coordinates, the next question becomes immediate. If the manifold is curved, how do we talk about directions at a point? In flat Euclidean space, this is easy. A vector can be pictured as an arrow. One can place it anywhere, slide it around, compare it directly with others, and think of all vectors as living in a common ambient linear space. But on a curved manifold, this global picture breaks down. A manifold itself is not a single linear space. One cannot simply subtract points everywhere or treat directions at distant locations as automatically comparable. So differential geometry localizes the idea of direction. At each point of the manifold, one defines a tangent space. This tangent space is a linear approximation to the manifold near that point. It contains the infinitesimal directions in which one can move away from the point. If the manifold is spacetime, then the tangent space at an event contains the possible infinitesimal directions of motion or influence through that event. A tangent vector is an element of this tangent space. There are several equivalent ways to think about tangent vectors, and each is useful. One may think of a tangent vector as the velocity of a curve passing through the point. In this picture, a curve on the manifold represents motion, and the tangent vector captures its instantaneous direction of travel at a particular event. Or one may think of a tangent vector as a directional derivative, an operator that differentiates functions in a specified infinitesimal direction. This second viewpoint is often more abstract, but it is extremely powerful because it does not rely on drawing arrows in an external space. Both viewpoints express the same local linear idea. The tangent space is where calculus begins to live on a manifold. This deserves slow emphasis. The manifold itself may curve. It may have a complicated global structure. But at each individual point, there is a tangent space, and that tangent space is linear. Linear structure gives us addition of tangent vectors and multiplication by scalars. It gives us the familiar algebra needed for differential calculus. So even though the manifold as a whole is not linear, each point carries a local linear model. That is one of the great organizing principles of differential geometry. Global curvature, local linearity. Curved overall, but linear in the infinitesimal neighborhood. This is why tangent spaces matter so much in space-time geometry. Motion, velocity, and differentiation naturally belong there. When a particle moves through spacetime, its instantaneous velocity is not simply an arrow in some universal background. It belongs to the tangent space at the point where the particle is. When one differentiates a field, one does so using local tangent directions. When one discusses light-like, time-like, or space-like behavior, these notions are expressed through the geometry inside each tangent space once a metric is supplied. So tangent spaces are not peripheral. They are the local stage on which geometric physics is written. But geometry needs not only directions, it also needs measurements. This brings us to covectors and dual spaces. A covector is best understood as a linear measurement device acting on vectors. If a vector represents a direction or an infinitesimal displacement, then a covector takes such a vector and produces a number. It does so linearly. In that sense, covectors are not directions in the same way vectors are. They are evaluators, probes, linear functionals. At each point, the collection of all covectors forms the dual space to the tangent space. This duality is conceptually important. Vectors tell us how to move or differentiate. Covectors tell us how to measure vectors in linear ways. The two belong together. Neither is more fundamental in an absolute sense. Each illuminates the other. For listeners first encountering this, the dual space may feel slightly abstract. So let us slow it down. Suppose you have a local notion of direction. That is a vector. Now imagine a rule that looks at that direction and extracts one component of information from it, linearly and consistently. That rule is a covector. It does not itself point in space in the same naive sense. Instead, it acts on directions. This might seem formal, but in physics it appears naturally. Gradients, for example, are more naturally thought of as covector-like objects. They measure how a function changes in different directions. Differential quantities attached to scalar fields fit naturally into the dual picture. From covectors one moves naturally to differential forms. Differential forms generalize the idea of covectors and provide the natural objects for integration or manifolds. A one form is essentially a covector field, meaning a smoothly varying covector at each point. High-degree forms measure-oriented infinitesimal pieces of geometry of higher dimension. They are precisely suited to the language of integration because they adapt to the geometry of the manifold itself. This is one of the quiet triumphs of differential geometry. It does not force integration to depend on arbitrary coordinate constructions. Instead, it provides geometric objects whose very purpose is to be integrated over curved surfaces and higher dimensional regions in a coordinate-independent way. For spacetime, this matters deeply. Physics often involves conservation laws, fluxes, volume elements, and integral quantities. Differential forms express such ideas with great clarity and flexibility. It is worth repeating that spacetime mathematics needs both vectors and covectors. Vectors capture directions of motion, flow, and differentiation. Covectors capture linear measurements and gradients. Differential forms generalize these measurement structures and support integration and geometric analysis. Together, they form part of the basic language needed to describe physical fields on a manifold. Once vectors and covectors are available, one can assemble more elaborate geometric objects. These are tensors. A tensor is, in broad terms, a multilinear object. That means it accepts several vector or covector inputs and produces a number, or another tensorial output, in a way that is linear in each slot separately. This definition can sound dry at first, but tensors are simply the natural bookkeeping devices of geometry and physics. They encode relations among directions, measurements, and local structure in a way that does not depend on arbitrary coordinate choices. A scalar field is the simplest example. It assigns a number to each point of spacetime. Temperature in a room is a familiar analogy from everyday physics, though in relativity one may use many different scalar quantities. A vector field assigns a tangent vector to each point. One may imagine a velocity field or a field of infinitesimal flow directions. A covector field assigns a covector to each point. More complicated tensors combine multiple vector-like and covector-like aspects into richer local data. The reason tensors are so central in spacetime geometry is that the key physical and geometric structures are tensorial. The metric is a tensor. Curvature is described through tensors. The matter content of spacetime is encoded in a stress-energy tensor. These are not arbitrary technical choices. Tensorial formulation is what ensures that the laws being expressed are intrinsic. They do not depend on a special observer or preferred coordinate system. They retain their meaning under smooth changes of coordinates. This is one of the main philosophical and mathematical lessons of the subject. Coordinate-independent formulation is not ornamental. It is essential. When we describe spacetime using tensors, we are describing geometry and physics in a form that survives translation between observers and coordinate systems. This is especially important in relativity, when no preferred global coordinate grid should be assumed merely for convenience. Among all tensors on spacetime, one has a uniquely central role. This is the metric tensor. The metric tensor is the object that turns a bare manifold into a geometry with measurable structure. On a manifold by itself, we know what smoothness means and how local coordinates fit together, but we do not yet know how to measure lengths, angles, durations, or causal type. The metric supplies this information. In ordinary Euclidean geometry, the metric allows one to measure lengths and angles in the familiar positive way. In spacetime geometry, however, the situation is subtler. The spacetime metric is not positive definite. That means it distinguishes different kinds of directions in a fundamentally new way. Some directions correspond roughly to motions slower than light, others to light-like propagation, others to space-like separation. The metric is what makes these distinctions meaningful. So the metric does more than measure size. It organizes causality. That is worth lingering over. In spacetime, geometry and causality are interwoven. The metric determines which events can influence which other events through causal propagation. It distinguishes the physically allowed structures of time and light from purely spatial separation. This is one of the reasons the spacetime metric is so much richer than a simple ruler. At the same time, the metric links vectors and covectors. It allows one to convert, in a natural way, between directional information and measurement information. It defines inner products of tangent vectors in the appropriate spacetime sense. It provides local notions of orthogonality, proper time along suitable curves, and spatial length in appropriate contexts. And in general relativity, the metric is not fixed once and for all. This is crucial. In special relativity, a metric has a standard flat form everywhere. In general relativity, the metric becomes dynamical in the sense that it varies from place to place in accordance with the physical content of spacetime. Gravity is encoded in this metric structure. Not gravity as an external force field sitting on top of geometry, but gravity as geometry itself, expressed through the way the metric changes across spacetime. So when one studies the metric tensor, one is already moving close to the heart of gravitation. Let us pause and summarize. We began by seeing why manifolds are needed. Flat spacetime is too rigid for gravity. We then introduced charts and atlases to describe manifolds locally without mistaking coordinates for reality. We introduced tangent spaces to recover local linearity and make calculus possible. We added covectors and differential forms to handle linear measurement and integration. We broadened the language to tensors, because the key structures of spacetime are tensorial. And now we have reached the metric tensor, the object that turns smooth structure into measurable geometry and causal order. From here, motion becomes geometric. To understand this, consider curves on spacetime. A curve is a continuous path of events, and in physics such curves often represent possible histories of particles or observers. But not every curve is equally natural. In flat Euclidean geometry, straight lines are distinguished by their simplicity and geometric character. In curved geometry, the natural analogue is a geodesic. A geodesic is, informally, the generalization of a straight line to a curved manifold. This phrase is common, but it should be handled carefully. A geodesic is not necessarily straight in the visual sense one might draw on paper, especially if the manifold is curved or if the coordinates distort the picture. Rather, a geodesic is a curve that is natural relative to the geometry. Locally, it preserves the relevant geometric structure. In many settings, it can be characterized as a curve that extremizes an appropriate length or time quantity. In other settings, it is the curve whose tangent direction transports itself in the most natural way. What matters here is not a single formula, but the geometric idea. A geodesic is the curve that spacetime itself regards as the unforced path. This becomes physically profound in general relativity. A free-falling particle, subject only to gravitation and no additional non-gravitational forces, follows a geodesic of spacetime. This is one of the clearest ways in which gravity becomes geometry. The particle is not being pushed off a straight line by a mysterious force. Rather, the geometrically natural path in curved spacetime is what we perceive as gravitational motion. It is worth repeating. Free motion in curved spacetime is geodesic motion, and geodesic motion is determined by geometry. This does not make gravity less real. It makes its interpretation deeper. Falling bodies are responding to the structure of spacetime itself. The local geometry encoded by the metric tells spacetime which curves are geodesics. Those geodesics, in turn, tell free particles how to move. So geometry shapes motion, and motion reveals geometry. But to talk carefully about how vectors change along curves, another difficulty appears. On a curved manifold, tangent spaces at different points are distinct spaces. A vector at one point does not automatically belong to the tangent space at another point. So what does it even mean to differentiate a vector field, or to say that a vector remains constant along a path? Ordinary derivatives are no longer sufficient. This is where covariant derivatives enter. A covariant derivative is a way of differentiating tensor fields on a manifold in a manner compatible with the geometric structure. It corrects the naive derivative by accounting for the fact that the ambient space may curve and that coordinate descriptions themselves may vary from point to point. This idea can sound technical, but the intuition is accessible. In flat space with standard coordinates, one can compare nearby vectors directly because the geometry is uniform and the tangent spaces can be naturally identified in a simple way. On a curved manifold, such comparison is not automatic. One must specify an additional geometric rule for relating nearby tangent spaces. The covariant derivative provides such a rule in infinitesimal form. This is why ordinary differentiation fails on curved spaces. It assumes too much global sameness. It assumes one can compare components directly without worrying about how the coordinate frame itself twists or how the manifold bends. Covariant differentiation repairs that by building in the geometric correction. Closely connected to this is the notion of parallel transport. Parallel transport asks the following question. If we move a vector along a curve, how can we do so in the most geometrically faithful way, trying not to twist or distort it beyond what the manifold itself forces upon us? On a flat plane, parallel transport around a loop returns a vector unchanged. But on a curved surface, carrying a vector around the loop may change its final direction relative to where it began. This failure to return unchanged is not merely an inconvenience. It is a signal of curvature. Parallel transport, then, is both a method and a diagnostic. It is a method for comparing vectors at different points along a path, and it is a diagnostic because the path dependence of parallel transport reveals the presence of curvature. Let us pause and reflect on the conceptual structure. Tangent spaces give us local linear worlds at each point, but those local worlds are separate. To compare vectors from one point to another, we need extra structure. Covariant derivatives encode infinitesimal comparison. Parallel transport encodes finite comparison along curves. And when these comparisons depend on a path taken, curvature has entered the scene. This leads naturally to the final major theme, curvature itself. Curvature is, in broad terms, the failure of flatness. That phrase is simple, but it carries a great deal. Flatness means that locally the geometry behaves exactly like the geometry of Minkowski spacetime, not just topologically or smoothly, but metrically and differentially in the appropriate sense. Curvature measures the extent to which this fails. In ordinary surface theory, one can get some intuition by thinking of spheres and saddles. But spacetime curvature is subtler and richer. It is not merely about how a surface bends in a surrounding space. It is an intrinsic feature of the spacetime manifold equipped with its metric and connection. It manifests in how geodesics behave, how volumes distort, how vectors parallel transport around loops, and how nearby free-falling particles move relative to one another. This last point is especially important physically. Gravity in general relativity is revealed through tidal effect. If two freely falling particles begin near one another, their relative motion is influenced by spacetime curvature. Even if each particle individually feels no force in its own local free-fall frame, the pair may drift together or apart because the geometry itself is curved. This relative acceleration is one of the clearest physical expressions of curvature. So curvature is not an abstract decoration added by mathematicians. It is the mathematical expression of gravitational structure. The Riemann curvature tensor is the central object here, though we need not write formulas to appreciate its meaning. Conceptually, it gathers together the different ways in which the manifold fails to be flat. It measures how covariant derivatives fail to commute in the naive way, how parallel transport depends on the chosen path, and how geodesics deviate from one another. In this sense, it is a compact repository of the local geometric content of gravitation. It is worth repeating that curvature measures how spacetime departs from Minkowski spacetime. Minkowski spacetime is the flat benchmark. In sufficiently small regions of a curved spacetime, one can often choose coordinates that resemble the flat picture to first approximation. This reflects the local nature of free fall and the equivalence principle, but only to first approximation. The deeper second-order departures, the tidal structures, the residual geometric effects that cannot be transformed away by a clever choice of coordinates, these belong to curvature. This is a subtle but vital distinction. Coordinates can remove some apparent complexity. They can simplify local descriptions. They can sometimes make gravitational effects disappear at a single point or along a specific path. But genuine curvature cannot be removed globally, and in general not even locally beyond the simplest order. True curvature is intrinsic. It is not a coordinate illusion. So once again we return to a recurring theme: the geometry must be distinguished from the coordinate. This principle has followed us from charts and atlases to tensors, from geodesics to covariant derivatives, and now to curvature. Let us gather the picture one more time slowly. A spacetime suitable for gravitation is modeled as a manifold because flat space is too restricted. A manifold lets us keep local Euclidean-style or Minkowski-style reasoning while allowing global flexibility and curvature. Charts and atlases let us describe the manifold using local coordinates, while reminding us that coordinates are only tools. The real geometric content must be independent of those descriptions. At each point, the tangent space gives a local linear approximation. This is where infinitesimal directions, velocities, and derivatives naturally live. The local linearity is what makes calculus possible even when the overall spacetime is curved. Covectors and dual spaces provide linear measurements of vectors. Differential forms generalize this structure and make integration geometrically natural. This gives us the language not only of local direction, but also of local measurement and accumulated quantity. Tensors organize these constructions into a broad and flexible coordinate-independent language. The most important structures in spacetime physics are tensorial because the laws of nature should not depend on arbitrary labels. The metric tensor then equips spacetime with measurable geometry. It defines lengths and angles in the spacetime sense, distinguishes causal types, and ultimately carries the gravitational field. Curves represent possible histories, and geodesics represent the natural unforced paths determined by geometry. Free-falling particles follow such geodesics, which is one of the clearest ways in which general relativity turns gravity into geometry. Covariant derivatives and parallel transport solve the problem of comparing vectors at nearby and distant points. They show us how to differentiate in curved settings and how the very act of comparison is shaped by geometry. Finally, curvature tells us how the geometry departs from flatness. It appears in tidal effects, in geodesic deviation, in path-dependent parallel transport, and in the deep mathematical structure of gravitational phenomena. It is worth pausing here and reflecting on how unified this all is. Differential geometry for spacetime is not a pile of disconnected definitions. It is a carefully interlocking language. Each concept arises because a previous one becomes insufficient. Manifolds are needed because flat space is too rigid. Tangent spaces are needed because manifolds are not globally linear. Curvatures are needed because direction alone does not capture measurement. Tensors are needed because the geometric laws must be formulated intrinsically. The metric is needed because smooth structure alone does not define spacetime geometry. Covariant derivatives are needed because curvature prevents naive comparison. Curvature is needed because gravity is more than local inertial simplicity. Every piece answers a genuine necessity, and this is perhaps the deepest reassurance for a student learning the subject. The abstraction is not arbitrary. The language grows because the phenomena demand it. Let us now come to a slow concluding summary. Spacetime geometry begins with the recognition that physical reality cannot always be described by one rigid flat background. To account for gravitation, we need a space that can curve, vary, and respond. That space is modeled as a manifold, locally familiar but globally flexible. On that manifold, coordinates help us speak, but they do not define reality. Many coordinate systems may describe the same spacetime. The true objects of geometry are those whose meaning does not depend on the chosen chart. At each event, tangent space gives a local linear world. This local linearity supports velocity, direction, and differentiation. Dual to it stands the space of covectors, measuring directions rather than merely expressing them. Differential forms extend this further into the language of integration. Tensors gather these ideas into a stable and coordinate-independent framework. Among them, the metric tensor is central because it gives spacetime its measurable and causal structure. It distinguishes the character of directions and encodes the geometry that gravity will use. Curves trace histories. Geodesics express free motion. Covariant derivatives and parallel transport tell us how local data changes across the manifold. And curvature finally reveals that gravity is not merely something that happens in spacetime, but something written into spacetime itself. So the mathematics of differential geometry becomes the natural language of relativity. Not because mathematicians sought complexity for its own sake, but because spacetime, when taken seriously, asks for a language that is local yet global, flexible yet precise, coordinate-based yet coordinate-free, linear in the infinitesimal yet curved in the large. And perhaps that is the gentle beauty of the subject. At every point, there is a small local simplicity. Around every point, there may be a larger global complexity. And between the two, differential geometry provides the bridge. That bridge is what allows us to pass from flat intuition to curved spacetime, from local observation to universal law, and from the idea of gravity as force to the deeper idea of gravity as geometry. Let us end there, with that unifying thought. The manifold gives the stage. The tangent spaces give the local directions. The covectors and forms give measurement and integration. The tensors give the language. The metric gives geometry. The covariant derivative gives comparison. The curvature gives gravitation. And together they form the calm and powerful mathematical architecture of spacetime.